Years ago on a diploma exam, we used to have 49 questions, 49 multiple choice and numerical response, and then 2 written response questions. Those 2 written response questions ended up being worth 15% of the exam each. They took those written response questions out, and for a time, it was just multiple choice numerical response, the old style multiple choice numerical response questions. But a couple years after they took the written response out, they introduced a new type of numerical response question. Same material, covers the exact same material, but the idea of this new type of numerical response question was to give you an opportunity in a way to show your work. It's still not the same as written response, not even close to the same as written response, but it does give you an opportunity for one question out of the 50 to show a little bit of process, to show a little bit of, okay, I know what's going on here, even if I can't get the exact answer. So today what I want to do is fairly quickly go through with you how we answer that question. Not the material, not the concepts behind it, because you know all that. We've gone through all that. There will be nothing new in terms of concepts over the next couple days. But today, again, show you how to answer that numerical response question when you get it, because there will be one of them. On your data sheet, I'm going to ask you to refer to that now. Bottom left-hand corner, you're going to see a list of 10 physics principles. They're also listed on the front of the handout that I gave you just a few minutes ago. 10 physics principles. There will be a question, as I said, on the exam that you have to solve, just the same as every other numerical response question. But the follow-up question of that will be basically, how'd you do it? Now, to describe how you did a numerical response question as a numerical response question, right? To describe how you did it, but express that as a numerical response question, they have to have kind of a unique way of doing that. They're going to list these, you're going to list these physics principles that you used in solving a problem from your data sheet. So let's take a look at those physics principles right now that you'll use, or potentially you'll use. Again, there's 10 of them. I want you to understand what each of them mean so that when you solve the problem, okay, just a matter of solving the problem and then looking at, hey, okay, what did I do? What did I do? Did I use physics principle 3 and 6? All right, write down 3 and 6. I just want you to make sure that you understand what each of those physics principles 3 and 6 and the other 8 of them actually are. Okay, physics principle 0, uniform motion. So that means if something's traveling at a constant velocity or the net force is 0. Forces are balanced. Okay, what can this mean? Balanced forces, constant velocity, suspended. Okay, we see that word suspended sometimes, or something that means the word suspended. Anything like that means net force is 0 or uniform motion. Okay. A situation like that might be a Millikan oil drop experiment where the oil drop is moving at a constant speed or is suspended. Okay. Another situation might be the cathode ray tube in the velocity selection chamber where the charged particle, the electron, goes straight through undeflected. The forces are balanced. Anytime an object is moving at a constant speed or a constant velocity, it's suspended, balanced forces, anything like that. Okay, there's forces acting, but it's not accelerating, then you're going to use principle 0. Now, I'm not trying to direct you how to actually solve a problem. You know how to solve the problem now. I'm just trying to direct you how to express how you solved the problem. Okay? Nothing I'm telling you today changes how you solve a problem. Again, all I'm telling you is how you express the way you solved that problem. Okay? Accelerated motion where the net force isn't 0. In other words, where the object is accelerating. Maybe you used F net is equal to the sum of the forces. Maybe you used F is equal to M times A. Bottom line is, if it's accelerating for whatever reason, then you're going to use the accelerated motion principle, principle number 1. So a situation like that might be a charged particle is accelerating, like a car going down a hill, although there's another principle that we could use in there as well. Okay, another principle might be, another situation there might be, again, the oil drop experiment, where an oil drop is accelerating upward or downward between the 2 parallel plates. We're using accelerated motion there. Uniform circular motion. Okay, I think that's a relatively straightforward one. Should be a pretty obvious one. The other one should be as well for the most part, but uniform circular motion. Object is moving in a circle, right? Okay, the most obvious example of that, the most obvious example of uniform circular motion would be when we have a charged particle moving through a magnetic field and it goes in a circle, right? Okay, that's uniform circular motion. Basically, if you introduce Fc equals mv squared over r, A is equal to v squared over r. By the way, Fc is equal to mv squared over r. Just a little aside here. We use that quite a bit, right? In the context of the main chamber of the cathode ray tube, or maybe just a charged particle going through a magnetic field. Remember, that equation is not on your data sheet. Okay? We know that A is equal to v squared over r is on your data sheet, and A is equal to F over M is on your data sheet. And if we combine those, A is equal to A, then we say, of course, F over M is equal to V squared over R, or F is equal to MV squared over R. It's not crazy hard, and we might even remember that equation, but just so you remember it's not there. Okay, don't look for F is equal to MV squared over R. You're not going to find it. If you use F is equal to MV squared over R, A is equal to V squared over R, or it's just an object going in a circle, and then we're going to say we use principle number 2. The work energy theorem, basically just the recognition that work is equal to the change in energy, the energy gained or energy lost. So if you got a situation, okay, where the object is gaining energy or losing energy, and you're talking about in the context of work, then you've used the work energy theorem. Maybe you've used W is equal to F times D, but you've been looking for the energy gained or the energy lost or something like that. We don't use W is equal to F times D very often in physics 30 because really that's a physics 20 concept. Okay, it's something that could potentially arise at some point, but it's not going to certainly be a major thing on your exam because it's not a physics 30 concept, it's a physics 20 concept. Conservation of momentum, I think that one's pretty obvious. Pi equals Pf, right? Whether it's one dimension or two dimensions, Pi is equal to Pf is a conservation of momentum problem. So that's principle number 4. Conservation of energy, we use fairly often, certainly in the context of a charged particle speeding up or slowing down, like a car going up or down a hill. EI equals EF, right? We're converting potential energy to kinetic energy, converting kinetic to potential, or some sort of combination of those. We're using principle number 5 there. Conservation of mass energy, that's a bit of a different one. How do you know when we've used that one? You get a question on an exam, and you're supposed to write down that you use principle number 6. What have we done that's told us that we've used principle number 6 there, Emma? Yes. Einstein's energy mass equivalence equation. Basically, that's it. If you use E equals mc squared, then you've used principle number 6. Now, conservation of charge, that's a bit of a different one because it's not a mathematical thing. Well, it is a mathematical thing, but it's like an addition thing as opposed to an equation thing. Okay, conservation of charge is just the idea that charge can't be created or destroyed. Sometimes you might use that if two things touch each other and the charge is balanced. Okay, that would be conservation of charge. Not a math problem really, right? Other than add them up, divide by 2, averaging 2 charges. Okay, a little bit of math, I guess. You know, maybe you rub two things together. They were both neutral. One becomes +5 and one becomes -5. That's conservation of charge. Okay. Another situation where you use conservation of charge will be when you're balancing a transmutation equation, a nuclear decay equation. When you look at, say, carbon 14, goes to a beta particle plus nitrogen 14. What else would be produced in that process, by the way? Yeah, good. It would be an antineutrino. The idea that these have to balance, the atomic numbers have to balance, that would be conservation of charge as well. Because look at it, right? You got a charge of +6. Okay, well, what do you have to have afterwards? You have to have a charge of +6. minus 1 plus 7 is equal to plus 6. So that would be conservation of charge. Conservation of nucleons, honestly, the only thing that I can think of right now that would express conservation of nucleons would be the top. You're making sure the number of protons and neutrons combined is equal to left side is equal to the right side. So nucleons, protons and neutrons combined have to stay the same, right? Well, we had 14 protons and neutrons over here. Hey, we got 14 protons and neutrons over here. It's a slightly different proportion, right? We had 6 protons, 8 neutrons. Now we have 7 protons, 7 neutrons, but the total number of nucleons, or protons and neutrons combined, have stayed the same. So charges stay the same, nucleons have stayed the same. And wave-particle duality. Okay, wave-particle duality. Compton effect and photoelectric effect express the particle nature of light. Okay, all those wave equations, like V equals F times lambda and so on, express the wave nature of light. Polarization, refraction, diffraction, interference, express the wave nature of light. If you happen to be talking about, however, the wave nature of an electron, that's de Broglie, right, the de Broglie hypothesis. If you happen to be talking about the particle nature of light, okay, then you're talking about wave-particle duality. That's a tough one for me to predict what you might see, okay, because we know that wave-particle duality is, particles have a wave nature and waves have a particle nature, but where are you gonna see that in a numerical response question? I'm not sure exactly where you'd see that, to be honest, in a numerical response question. But understand that's the concept that it represents. Okay? And if they happen to throw something at you, just recognize, oh wait, okay, we didn't predict that, but that's still the concept that it represents. As long as we know what it means. All right, what I want to do now is go through a couple of examples of numerical response questions that use these principles. Now, having said that, I'm going to pick the ones that I've photocopied for you, and the ones that I'm going to do here in class today tend to be, on average, harder than the ones that you get. Okay, when they started doing this, when they started introducing this type of numeric response question, they made them hard. Like they basically took a written response question and turned it into a numeric response question. And they were hard. For one question, for one numeric response question that's worth 2% of your exam, they took written response questions that used to be worth 15% and then just changed it into a numeric response question. And I think they realized that that wasn't entirely fair. I think they realized that that was too much work to do for a numeric response question. Having said that, we're going to go through a couple challenging ones. I don't think the one that you'll see will be as challenging as the ones that we go through, but I would rather go through hard ones and have you see easy ones than go through easy ones and have you see hard ones. Does that make sense? So, if the questions that we go through you find a little bit challenging, okay, don't panic about that. Hey, don't panic about that, because in the end, they probably won't be as hard as that. And hey, worst comes to worst. Worst case scenario, you get this question wrong on the diploma exam. How much have you lost? 1 point. 1 point out of 50. Right? It's not the end of the world. Okay, you're probably not going to get 100 anyways. Okay, if you lose a point, lose 2%, it's not the end of the world. Having said that, if you get the question wrong, you can still get the follow-up question right. Okay, you may know 2 concepts that you use to solve the problem. You may just not have been able to solve the problem. So you can still, you're not going to lose automatically 4% as a result of getting this question wrong. Okay, it's only 2%. The follow-up questions, you should still be able to get right. Devin? Sorry? Well, it's 2 numeric response questions that go together. The first numeric response question will be, basically answer this question, just the same as any other numeric response question. But then the follow-up question of that will be, what are the 2 physics principles you used to solve that problem? No. The 2 questions, you mean? No, each one of them are worth 1 point or 2%. So it's a total of 2 points out of 48. But the first one, it's not like it's not unlike any other numerical response question, right? So I don't really separate that one, right? That's the same as any other numerical response question, worth the same, whatever. The follow-up question of that is also worth a point, and that is, what are the two physics principles you use to solve it? Now, sometimes there might be three. Okay, that's good news if there's three, because you got some options now. Maybe you're not sure about something, don't pick it. Okay, if there's three principles you use, just pick two. And the good news is, hey, when they first started this, they made you list them in the order that you used them. That was stupid. It was stupid because we all solve things differently. Now, there was a system that I had that allowed us to kind of play the game, okay, that allowed us to answer it in the correct order that they expected it to be listed, even if you didn't actually do it that way. Okay, we had a way of determining which way they expected to have them. Now we don't need to worry about that. Now if we get the two physics principles, it doesn't matter what order we list them in, we're still going to get it right. Okay, make sense? All right. So let's take a look at an example here. The first bunch of examples in your textbook, or sorry, in the handout that I gave you, are actually graphing questions. And I want to look at some graphing stuff tomorrow. If we have time, maybe a little bit later today, but that's not my focus here today, okay? We've looked at graphing quite a bit, okay? And again, I'd like to review it because we will get a graphing question on the exam as well, worth 2%. But that's not my number one priority, okay? That's number two priority. So let's fast forward to page, let's go to page 11. Actually, you know what? Let's not go to page 11. Let's go to page 12. The reason that, yeah, let's go to page 12. So we're looking for this question right here. What I'd like you to do now with this question on page 12, and it carries over to page 13, where you have the actual two questions, right? The magnitude of the electric force and then the two physics principles used. What I'd like you to do is just take maybe 5 minutes at your desks right now, sit down, 5 minutes at your desks, and try to identify some things you know about this. If you get a chance to actually start solving it and even get the answer, that's great. Okay, but that's not the main point of this right now. Okay, I want you to identify, okay, what would I do? What are some of the things that I could try for this? And I want you to see that even if you can't actually solve this problem, you may still yourself be able to get the follow-up question, identify the principles, okay? So 5 minutes right now, see what you can do with it, and then we'll take a look at it as a group here, okay? Let's take a look here. As you read through this, is there anything, first of all, that didn't make any sense to you? Okay, is there anything that jumped out at you? Maybe a word that led you to some principle or some concept or just some idea that maybe you had, yeah? Okay, it undergoes alpha decay. So let's circle that to draw our attention to that. Okay, maybe we have to write a transmutation reaction there. Maybe we have to balance things out. Maybe we're going to do a conservation of charge thing there or conservation of nucleons thing there. Okay, maybe. Okay, maybe not. We don't know for sure yet, but Simon? Okay, parallel plates. Oftentimes when I see parallel plates, one of the things that comes to my mind right away is E is equal to delta V over delta D. We don't know for sure that we're going to use that right now, but that's something that definitely came to my mind. Is that what came to your mind when you saw parallel plates? Okay. We know it's definitely an option for us, right? Whether we end up using it or not, it's an option for us. So at least, you know, somewhere down the road as we're solving this problem, you know, we've got something to try. We're not like, what the heck, I'm done. I can't think of anything to try now. We got something to try. Yeah, Emma? Okay, said that somewhere here. Where does it say that? Oh, here we are. Yeah, here we are. So the alpha particles are stopped. Now, what did that tell you anything, like maybe what we can do, or? Be careful with that, okay? It ends up being the same equation. It ends up working out, but EK max is equal to QV stop is a photoelectric effect equation, okay? The idea of charged particles slowing down or stopping is a conservation of energy problem. It's like a car going down a hill. So we'll say EI equals EF, but just be careful that you don't mix it up with the photoelectric effect, even though you might have ended up solving it correctly there with that equation. You might not have, you may have or may not have. EI equals EF. Okay, perfect. Anything else? There's one word in here that when I read it, it just hit me. When I saw the word isolated, that all of a sudden reminded me of something that we did in Physics 30, where we talked about isolated quite a bit. Remember what that was? I got a nucleus here that's sitting there, and then it's decaying. So one piece of the nucleus goes one way, the other piece of, thank you, the other piece of the nucleus goes the other way. And it's an isolated system. That struck me as an explosion, where maybe we have conservation of momentum. Why else would they tell me that it's an isolated system? We have to have an isolated system in order for momentum to be conserved, right? Why would they bother telling me it's an isolated system? They gave me a hint there. They told me, in a sense, that it's going to be an isolated system. Or sorry, that it's going to be conservation of momentum. So I got lots of things here now. And listen, if you don't know how to solve this problem, you don't know where to go with this, guess what? You can still get the next question right. We've got enough things listed here right now, enough valid things, that we can answer the second question, which asks us to list the physics principles. All right. Let's solve this problem now. Just don't have very much space. Oops. That's not what we want. Okay, let's see what we can do on just on the side here. All right. Since the first thing that kind of came about here, as far as numbers go, Simon caught the first thing there, parallel plates, but up here we don't know anything about those parallel plates. Okay, the first thing that kind of came about for me numerically was up here. Okay, the whole isolated system, the whole nucleus decaying. Listen, when a nucleus decays, it is a conservation of momentum problem. Okay, it's just like firing a gun. A gun and a bullet are one object, they become two objects. This nucleus, thorium-226 nucleus that was sitting there, decaying into radium-222 and an alpha particle, it's like the gun going one way, the bullet going the other way. It's no different. We can say Pi equals Pf, and we can therefore say zero initial momentum equals m1 v1f plus m2 v2f. Boy, it's been a long time since you've done that, eh? Does it kind of ring a bell, though? Back when we did our momentum unit, we never did any kind of nuclear decay for conservation of momentum. Why not? Because you didn't know what nuclear decay was. You didn't know what a nucleus was and what an alpha particle was and so on. So the mass one is the mass of the thorium. Sorry, the mass of the radium. Doesn't matter what the mass of the thorium is. We don't know what it is. Doesn't matter because 0 times the velocity, 0 times whatever the mass is 0. The mass of the radium after it decays, 3.67 times 10 to the minus 25, and it moves to the right at 3.1 times 10 to the 5. Plus the mass of the alpha particle, 6.65 times 10 to the minus 27 times the final velocity of the alpha particle. So what have we just found here? The final velocity of the alpha particle worked out to be 1.7108 times 10 to the 7 meters per second. Usually we say charged particles are in the range of 10 to the 5, 10 to the 6 meters per second. Is this possible? Sure it is. If you got a number here that was 10 to the 8 or 10 to the 9 meters per second, you made a mistake somewhere. Okay, but this falls right in that range that we would expect to get. 10 to the 5, 10 to the 6, 10 to the 7 meters per second. And I'll tell you what, When I solved for that, when I got the final velocity of the alpha particle, I thought, hey, I think I'm on the right track here. Because if you read the question, it says, what's the the electric force on the alpha particle? I just solved for something about the alpha particle, and I'm looking for something about the alpha particle. It's not the same thing, okay, but it's something about the same thing, about the same object, same alpha particle. So it told me that I'm probably on the right track here. No guarantees, but certainly, hey, even if this doesn't help me, I haven't done anything wrong, right? This is a correct thing to do, whether it helps me or not. And I think that it will help me. Emma said EI equals EF. Hey, you don't know what to do next? Try what Emma said. Okay? Try what Simon said if you want, but you don't know what delta V is yet, right? So as much as you might write down, E is equal to delta V over delta D. We don't know what delta V is, so not helpful, at least yet. Maybe it'll never be helpful. I don't know. Let's try Emma's EI equals EF. It starts off with kinetic energy, doesn't it? Because it's moving. After the explosion takes place, it's moving 1/2 mv squared. And then it ends up with, as it slows down and stops, it ends up with just potential energy. So kinetic converted to potential. Hey, this alpha particle is slowing down and stopping. It's like a car going up a hill. Kinetic is converted to potential, except it's not gravitational potential, it's electric potential. The mass of the alpha particle is 6.65 times 10 to the minus 27. The initial speed we just got. The charge of the alpha particle, 3.2 times 10 to the minus 19. The final potential. That's not final speed, right? That's final electric potential. And it works out to be 3.0413 times 10 to the 6 volts. Wait a second. Simon, I just told you we can't use E equals delta V over delta D yet because we didn't know what the potential difference was. Now we do. So let's try Simon's thing now. Okay, let's go back to the E is equal to delta V over delta D and see what happens here. Okay, let's do that over here. I don't care if, hey, this question, if you've got stuff all over the place on your page, that's fine. Okay, you're not actually showing your work. Okay, I want you to write it all down, but if it's, hey, if I don't have enough space and I write E is equal to delta V over delta D over here, that's fine. Delta V, well, the final potential is 3.04. The initial was 0, so the potential difference is 3.0413 times 10 to the 6, divided by the distance between the plates, which was 2 centimeters, 0.020 meters. Okay, that gives me an electric field of 1.5206. Oh my goodness. It seems like we're kind of dancing around what we need to do here. We're looking for the electric force on this alpha particle. We've done 3 calculations and we still haven't got it? But you know what? There's 4 parts to this question, and we've just done the 3 hardest parts. Funny enough, the easiest part is coming up, and it might be the part that we kind of struggle finding a little bit. Okay, but you shouldn't. Just take a step back from it for a second. We're looking for the electric force on the alpha particle. We didn't know how we were going to find the electric force. We just did something that we knew was valid, something else that we knew was valid, something else that we knew was valid. And lo and behold, we come up with the electric field that acts between those plates. We want to find the electric force on the alpha particle. It's Q times the electric field. It's 3.2 times 10 to the minus 19 times the electric field that we just got, 1.52, and so on. Gives me a value of 4.9 times 10 to the minus 11. That's a long question, and that's a hard question. And a question like that, when they introduced this type of numeric response question, was fair game. And I wouldn't say I'm 100% sure that you won't see something like that this time, but I'm pretty sure. Okay, the pattern over the last few years has been easier numeric response questions for this. It's just too much work for a numeric response question. If they're going to give you a question like this, they need to give you the extra hour and a half that they used to give you for a written response. Okay, they can't, in all fairness, expect you to do something like this in the time that you were expected to do just regular multiple choice numeric response before. Is your hand up, Brian? Now, that's not the only way to solve this problem. It's not. Okay, we got to do PI equals PF, whatever's in green there. I don't see any other option for that. But there's another option past that. Okay, I'm not gonna actually solve the other option, but I'll just kind of write down what it would be. Okay, once we get this, we could say maybe VF squared equals VI squared plus 2AD. VF would be 0. This charged particle, it's slowing down, right, and stopping. VF would be 0. VI would be 1.71. A, we don't know what A is, but it slows down over a distance of 2 centimeters. So we could say 0.02 meters. You get the acceleration. I don't know what that works out to be, but we could get it. And then once we have the acceleration, F is equal to m times A, right? Guess what we'd get? Mass of the alpha particle times the acceleration, we'd get 4.9 times 10 to the negative 11 newtons. So if you do it the first way, okay, if you do it the first way, what is green, red, and blue, what principles would you use? Look at your sheet, all 10 physics principles, and I want you to tell me which 2 physics principles you used, or that we used. Remember, it's green, red, and blue, not the purple there. Okay, that was the second method. Green, red, and blue. What 2 physics principles did we use? Tell me one of them. Yep, Daniel? Conservation of momentum, good. And what principle number is that, Daniel? Okay, so principle 4. What else did we use besides conservation of momentum? Yep. Conservation of energy. What principle number is that? Principle 5. So you could list that as 4, 5, or 5, 4. Make sure you start in the first block, right? Not the second block, not the third block. Don't leave anything blank at the beginning. You're going to leave something blank, leave it at the end. Yep. You got 4.8. Okay, so did I? Let's see here. Yeah, Tom, mine must have been a rounding thing or something, so it would have been, so Emma's getting 4.8 as well, so. Did you solve it the way that we solved it, Emma? Okay. I didn't even notice the answer was there, to be honest, Tom, but good thing I solved it correctly, except for the rounding thing. So we got 4, 5, principle 4, 5. Right? Could you say 5, 4? Sure, sure, doesn't matter. Okay, let's say we solved it, though, the purple way. Okay, we come out of this. Daniel solves it the green, red, and blue way, gets 4 or 5, principles 4 or 5. Then Emma comes out of it, says, no, I didn't do it that way at all. I did it the purple way. What principles did we use there? 4 and what? 4 and 1. Right? Accelerated motion, principle 1, and still conservation of momentum. So 4, 5, 5, 4 would get you a correct answer there. 4114 would get you a correct answer there. If we look hard, we might even be able to find something else. I'm not sure, but those are the obvious ones. By conservation of charge? How so? Yeah, yeah. Now, are you saying, could we solve the problem? Could we? I don't think so. Yeah, I don't see a way that you could do it that way. Hey, we identified, I think it was Maria, that first thing she spotted was maybe there is some conservation of charge in there, right? Because there's an alpha particle produced, and you maybe have to balance a reaction. Turns out we didn't end up doing that. It was certainly something that was valid that we could have tried. Didn't end up doing that. And honestly, Simon, I don't see a way that we could have ended up getting our answer that way. Let's have a look at the one on page 11 now. Quite a bit different than the one that we just saw. Have a read and see if in the next 3 or 4 minutes you can think of something to do here. Maybe a concept that applies, a principle, maybe just a word that jumps out at you. Like in the last one, we saw that word isolated, right? That jumped out at me. Okay, is there anything that jumps out at you? Is there anything that just doesn't make sense? Any words that don't make sense to you? Okay, take 3 or 4 minutes, and then we'll take a look at it as a group again. Let's take a look here now. This one says electrons are accelerated from rest by a potential difference of 300 volts. Electrons enter a region that contains electric and magnetic fields. The electric field has this value, the magnetic field has this value. And then the question asks us, what's the acceleration? What's the acceleration of the electrons as it first enters here? Okay, at this point, what's the acceleration of these electrons? Okay, is there anything, first of all, that didn't make sense to you here? Any words that didn't make sense? Any concepts that didn't make sense? Whatever? All right. Is there anything that jumped out at you? Any concepts that you think might apply here? Whether you're going to end up using them or not? Anything that any key words like that isolated system thing that lead us to something here? Simon, what's one thing? Okay. So what does that tell you? Okay, so if you've got a perpendicular electric and magnetic field, then you've got probably an electric force and a magnetic force, right? The electric force is equal to Q times E, the electric field, and the magnetic force would be equal to QVB. Let's take a quick look here. The electric force would be acting up on that particle. The magnetic force would be acting down, right? Thumb, fingers, palm points downwards. Okay. Simon, we don't know for sure right now whether we're going to end up using that, but if I've got that much information about these electric and magnetic fields, including directions here, I think there's a good chance that I'm going to end up using that. Okay, we don't know for sure, but we don't have to know for sure. It's something that we can try at least. Okay, is there anything else that jumped out at us? Or even that maybe wasn't quite so obvious, but was a little bit more subtle? Yeah. So the electrons accelerate? Okay. That's the first thing that I saw too, was the electrons accelerating from rest by a potential difference. What does that tell us? Okay, yeah. Not so much the concept per se right now, like the principle that you're looking for in your data sheet right now, but what are we going to do? What do we do every time a charged particle speeds up or slows down? It's like a car going down a hill. What do we do? EI equals EF. Okay. Now, it's probably not the only way. Maria said accelerated motion. We could probably use F is equal to, we could probably use a bunch of different stuff in there, but that's the first thing that comes to my mind. Every time I see a charged particle speeding up or slowing down, no matter what the context, I think EI equals EF. Always. Now, there is the odd time when that just doesn't work out for me, but I always think that. Anything else? What are we looking for here? The instantaneous acceleration. What do we do always in physics 30? Always in physics 30. When we're asked to solve for acceleration. Yep. Okay, answer my question, then I'll get you. We get the force and then solve for acceleration, right? If you want acceleration in physics 30, you're going to use F equals ma, almost certainly. I shouldn't say that, not 100%, but 99% of the time, you're going to get a force and then solve for acceleration. Simon, what else are you going to say? It's a negative particle. Right? No, you're not using a hand rule for an electric force. Hand rule is only for magnetic force, right? And a negative particle will experience a force opposite to the field. Now, which way is the field here? Well, the field is going downwards, right? From positive to negative plate. So if the field is downward, the force on the electron will be upwards. Think about it this way. You got a negative particle right here. It's attracted to the positive plate, right? Remember the hand rules? Okay, the hand rule we use for the magnetic force, thumb, fingers, palm. But that's all we use the hand rules for is the magnetic force. Okay, let's see. You guys seem to be kind of stalling here in terms of what we can do here. So let's start solving the problem here. Okay. Now the first thing that appeared here chronologically in this thing that Maria spotted, the electrons accelerated. Let's try the whole EI equals EF thing here first. Okay. We know that Q EI equals EF. We know that Q times V, the potential energy that we start with when the car is at the top of the hill, right? Car going down a hill, is equal to the kinetic energy of the car at the bottom of the hill. It's an electron, so the charge is 1.6 times 10 to the minus 19. The potential difference is 300 volts. Mass of the electron. Solve for V works out to be 1.0265 times 10 to the 7 meters per second, which, hey, right in that range that we expect to get, right? 10 to the 5, 10 to the 6, 10 to the 7 meters per second. All right. Got a speed. How's that helpful to me? Well, the first thing that Simon spotted was this whole electric force and magnetic force, right? The magnetic force depends upon speed, right? So that's probably where we're going to go with that. We just got the speed of the electron. Simon said we're going to need to find the magnetic force, which depends upon the speed of the electron. So maybe let's do that. But you know what? Before we do that, let's recognize, no, let's do that. Let's just do it. Okay, let's just get it. The magnetic force is QVB. It's 1.6 times 10 to the minus 19 times the speed that we just got times the magnetic field strength, which is 2 times 10 to the minus 1 Tesla. I get 3.2848 times 10 to the minus 13 newtons. Simon didn't just say there's a magnetic force. He said there's an electric force too, right? We just found the magnetic force. If it's going to be relevant to us, then probably the electric force will be as well. So let's get that now as well. Even though we didn't just solve for a speed to get the electric force or whatever, let's do it anyways here, okay? Fe is equal to Q times E. So it's 1.6 times 10 to the minus 19 times the electric field, which is, can't see that, 8 times 10 to the 5, 8.5 times 10 to the 5. That gives us 1.28 times 10 to the negative 13 newtons. Oh, wait a second. Wait a second. Things are starting to fall into place. We just found a couple of forces, right? What did we say we had to do to find acceleration? Get a force, right? Which force, though? Is it electric or is it the magnetic force? Or, Maria, is your hand up there? Did you get a different number there? for the electric force? Yeah, I used 8 instead of 8.5, so you're probably right there. What is it, 1.36? Okay, thank you. Which force do I use? Okay, I'm so close. I can taste it. I need a force to find the acceleration. But which force is it, electric or magnetic? It's both of them, right? It's both of them. F equals m times a. F is the net force. Okay, so let's now say, if you want, F net or m times a, right? The net force is m times a equals the sum of the forces. It's the electric force plus the magnetic force. Okay, the mass here, 9.11 times 10 to the minus 31 times the acceleration. That's what I'm looking for. The electric force is upwards, so it's positive 1.36 times 10 to the minus 13. The magnetic force is downwards, so it's negative 3.28 times 10 to the negative 13. And we solve for A. We end up getting negative 2.11 times 10 to the negative 17 meters per second squared. Now, they asked me to express that as A decimal B times 10 to the negative CD. We'd express that as 2117, right? 2.1 times 10 to the negative 17, 2117. This is an easier question than the last one, isn't it? But it's still not easy. It's still not easy. Okay? This is something that I still think, to be honest, is a little bit harder than you'll probably see. But I'd be less confident in saying that than I certainly was on the last question. Okay? That's a doable question. It's a tough question, but it's a doable question. Okay, what principles did I use? Yep. I used conservation of energy, definitely. And what principle was that? Okay, so I used principle 5. Good. And what else did I do? Maria? I used accelerated motion, which is principle 1, I think. So 5 and 1. So we could write down the follow-up question 5, 1 or 1, 5. Now, there was a time when you would have had to write 5, 1, or you would have gotten it wrong. 1, 5 would have been a wrong answer. But now 5, 1, 1, 5, they'll count both of those. Yeah. Yes, but there'll never be a time when you have to express more than 2. So if you use 3 or 4 principles, that's great, because then it gives you even more options, right? If there's one of them that you're just like, oh, geez, is that principle 6 or is that principle 5 or whatever the case may be, right? Then you don't have to pick that one. So it's always going to be list 2. Do you know what's funny? When the first time they gave the exam with this type of numeric response question on there, the physics principles weren't listed 0 through 9. They were listed 1 through 10. And I spotted that right away. You know what I told my students that year? I said, they always tell you, express your 2-digit answer, blah, blah, blah. I told them, if they tell you express your 3-digit answer, then one of the principles is principle 10. It's the only way to get 3 digits with 2 principles, right? Is if it was principle 10. Well, I don't think I was the only one that spotted that, because the next exam they renumbered them 0 through 9 instead of 1 through 10. At that time it could have conceivably been a 3-digit answer, but it still would have been 2 principles. Okay, it'll always be 2 principles. So now it's always going to be first 2 boxes, fill something in, last 2 boxes, blank. Got it?